Alright, so now we're back in the workbench here. So just like the last couple videos, how we're talking about the ping pong algorithm and the top 5 of 15, how there is like a wire sheet version, and then we vibe coded some program objects, and then we tested the behavior of the algorithms in the same fashion. So we just verified that the algorithm behaved the same way as wire sheet logic. We can do the same thing with Guideline 36 VAV box. So stay tuned. Okay, so here we are. So in Workbench, we have some points here. So this would be the temperature request points, like the spec we were just looking at for Guideline 36. Here's a zone cooling set point, a zone temp, and a zone demand. This is in my office test environment, so there's no drivers, no actual real field devices, but we can just have some generic points here just for creating algorithms. So the temperature request points, zone cooling set point, zone temp, zone demand, like we talked about, and then here's the requests for cooling. Satisfy that, and then here is the VAV air damper command, VAV flow set point, and then this is our final output for pressure requests to calculate system variables. And then also the wire sheet logic is let's look at the pressure request. So like what we were saying before, there's we need to be able to send 3 requests based on 50%. So there's one part of the spec that to send 3 requests if the airflow is within 50% of the set point, and if the air damper is greater than 95% command. So this is like what wire sheet logic looks like to generate requests. And then there's also some delay timers. So like the specs also talk about that these conditions, that there's a demand on the system, and it needs to have a delay in there to basically kind of time things out a little bit better for a mechanical system. So this is pressure request logic. And then same thing with the temperature request logic, that wire sheet is written in similar fashion of a 1 request constant, 95%. So like if I can't remember what this one is, so send 2 requests. So basically this one is zone demand. If the zone demand is greater than 95%, send 1 request, else 0. So this is the same, it's pretty similar, easy little spec to create. It's actually pretty simple little wire sheet logic and works fine in wire sheet logic. But we can do this in Java as well in a ProgramObject. So let's experiment now with our algorithm behaviors. The only thing that might be kind of hard to do is the timers. Alright, so this VAV is already in 3 requests here. So our simulated zone temp is 78 and our set point is 72. So in the real world, we're actually way above set point. So we'd be calling for cooling. So that's why we're generating 3 requests. So if we put this back down to, let's say, 72.5 and zone demand of 0, our cooling requests go to 0. So let's put our cooling demand up to 100, and that goes to 1 request. So let's look at the spec and just make sure that if our zone temp is around the set point, what happens if our zone demand, which I don't think this would ever happen in the real world, but so we're pretty much in a deadband mode here, but our zone demand is 100%. Let's see what our spec says. So if the cooling loop is, so here we go. So if the cooling loop is greater than 95%, which we are, send one request. So that's what we're at, and this part is satisfied. So if the zone set point exceeds the zone cooling set point by 5 degrees for 2 minutes, that's when we would count 3 requests. So right now we have this part satisfied. We have 1 request. So if we really crank up our zone temp to be 5 degrees above, simulate 80. If we jump back into here, we should be, so this is true, sending 1 request, and then we should immediately be in here in this mode. So for 5 degrees above, which we have a constant for that, and we are, so our simulated zone temp is 80. That is true, so we have to satisfy that 2-minute timer. So this is once that 2-minute condition expires, this will switch, and then we'll send 3 requests to this maximum block. So that's our temperature request logic. So this will satisfy. This will bump up to 3 after that condition satisfies. So on the pressure request logic, same way. We just have a maximum block. Very similar wire sheet logic. So let's just simulate the behavior of this. Alright, so we're at 0, even though that we're way under airflow set point. So 970 CFM set point, and we're only at 202 right now. I'm surprised that we're not calling for 1 request. Okay, so this is actually just the air damper position needs to be above 95% to send 1 request. Really similar to here, if the cooling loop is above 95%, send 1 request. So same thing with air zone temperature set point. If the measured volume of air, the airflow, is less than 50%, send 3 requests. Okay, so right now we must not be below that 50% value. So this is kind of important that we need to be, if the measured volume of air is less than 50% of set point, while set point is greater than 0, and the damper position is greater than 95%, then send 3 requests. Okay, so what's important in this algorithm is that the air damper position needs to be greater than 95% for a minute. Alright, so let's check our pressure request logic. Alright, so this is where we're multiplying by 50%. So this is our set point of 970 CFM. So this is how we're calculating 50%. And right now we are definitely way below than 50% of the set point. And what needs to happen is that our air damper position needs to be greater than 95% in order for us to start calculating. So as soon as we, as soon as we crank up our air damper position to 96%, that's when our algorithm will start generating requests to satisfy the spec. So I don't think I'm going to sit and wait for all these timers to expire, but that is kind of the nuts and bolts of how Guideline 36 systems requests work. So we kind of study this, and then we we just look at the algorithm's expected behavior and when we validate this. So let's see if we can do this in a little bit of Java now. Even though that these are easy enough to do in Wiresheet logic, I think this would be like a nice easy application to do in a Java program object where we could combine both of these in some Java code and then also test it and then make sure that we have same expected algorithm behavior. Plus I think this could be a nice driver at some point in time, or a module in Tritium. So like we're kind of marching down that path of doing wire sheets, a program object, and maybe someday even a driver. Alright, so here we are again. Let's start laying the groundwork for a program object. And the thing that gets kind of messy is that this is a snip of the Guideline 36 and ASHRAE documents, and ASHRAE does not want their documents to be uploaded to AI, which is kind of unfortunate. So, but we can maybe just describe it in chat to ChatGPT, and maybe even take some screenshots, which ChatGPT can understand Wiresheet logic pretty well. So let's start laying the groundwork for this in chatting with AI. So, all right, so let's ask ChatGPT. So, I want a program object for system level request counting on a VAV box for both pressure and temperature requests based on actual Guideline 36 logic. Alright, so this is how it might get kind of messy. I'm just kind of seeing this, making this up on the fly. Snipping tool, where are you? So I am going to just start snipping stuff. Let's see if this will work. Go off of these snips. I'm uploading to you on a Wiresheet version where we want to mimic a program object in the same fashion. So let's see, the Wiresheet has folders for temperature and pressure counting logic for requests, but our program object should handle all of this internally. And maybe start with this. Can you see these inputs and lay the groundwork for this? Alright, maybe we just start here. And then once ChatGPT can kind of come up with the Java logic, let's maybe we could get a little bit more details on the internal, because basically we want a program object that will replace both of these, and it'll just have one here. Well, we'll just link everything here and here, and I'm just a little bit hesitant on giving it too much information right now. So maybe if it can just lay out the slots and some generic logic, we can then keep pushing AI to revise the code inside, and then obviously test it for the expected behavior. Alright, here we go. So propose slots for pressure and temperature, that's what we want. Output slots So I don't think what we want is anything tunable. So I'm actually gonna have it, because these are actually, see these numbers right here? These are actually hard-coded in the spec. So I'm gonna ask for, push it one more time to revise it. Can you just hard code Java for the tunable these things, the tunable features? Don't make slots for these, for the I'm just gonna say they should be hard-coded. Usually in computer science, they do constants in all cap inside the program objects in Java land. Please update code and new slots to handle no tunable variables. Okay. I'm not even going to look at the code that it generated, so see if it'll do this one more time. So AI is thinking, and you know what we can do is actually duplicate this here. So I'm going to call this our program object. So, and also on the repo, like I'll all these pre-built wire sheets will be available to download as a BOG file. So just I'll show you. I'll leave a link in the show notes, just like where this stuff exists. So there'll always be a wire sheet version, and then there'll always be a program object version. So including like the full-blown Guideline 36 for air handling unit 2. Alright, so I'm gonna jump into here, program object version, and then like the last videos, it's delete you and drag out program object for system level requests. Okay, so let's see what we got here. Alright, so execution period, zone demand, no separate, gosh, execution period. Let's see, so that should be an internal timer. Sure, why not? So every 10 seconds that there's an internal timer that it'll execute. I don't know if that needs to be adjustable from the outside world, but maybe. Alright, so it says actually we still have to tell it like what it'll do with these. So default looks like. Alright, so it kind of laid out some boilerplate code for us. So let's build a program object. VAV is kind of an odd looking variable. Maybe it didn't quite get the. I'm gonna ask to update this. Update the name of to the D on the end. Okay, so let's start going to town here. Slots, so our VAV damper command. Summary, status numeric. We want to be able to wire into that. VAV flow. Summary, status numeric. Flow set point. Also a status numeric. Cooling set point. Zone cooling set point. Status numeric. zone temp, status numeric, and also this zone demand point is 0 to 100% command. That's also one that can be terminal load. I've also seen it defined like that. And then also here's VAV pressure requests. These are outputs, so this will be read only, status numeric, cooling requests. Read only, status trace. Kind of like these status traces. Read only. Where are you? Status string. And then this is this internal execution period. I might leave this out. That can just be hard coded into the back end, just internally, how often this algorithm updates, and also just make internal constant fashion. I suppose we could start describing a little bit on how we want our pressure processes to work. So I'm kind of like a big fan of just giving screenshots to ChatGPT. So if I go back into here, here's our pressure control logic. I bet that just giving ChatGPT screenshots. Thing is I need to like put these logic blocks a little bit closer together so I can get them all inside one screenshot. I've tested this before, that I do think that AI is pretty good at looking at screenshots of wire sheet logic, which is kind of interesting. So let's just get these a little bit closer to clean this up a little bit, and then we should be able to get this all on like one snip, which okay, so this will be, and we'll just describe this all in written form. So you know what I might do, well actually I think this will be fine. So I can grab, hold up, I might just do one thing in here. So I can grab the name of this. Let's just ask it to update. Get a nice, well, maybe one more nicer screenshot. Also getting the tab of the name of that. So let's ask it here, can you update the program object Java code to be an exact mimic for the screenshot of the working wire sheet logic? So you should be able to understand that. Let me know if that does not make sense. Okay, so maybe we could even describe it here. This, it would be so nice to be able to upload that. Then it would just know. So I'm actually just going to try and fat finger it in here. So I'm just going to tell it, just do pressure for the moment. Looking at the spec here, if the airflow is less than 50% of set point, while set point is greater than 0, and the damper position for the VAV is greater than 50% for 1 minute, that equals 3 requests. Else, if the airflow is less than 70% of set point, while set point is greater than 0, and damper position is greater than 5% for 1 minute, send 2 requests. Else, if the damper position is greater than 95%, send 1 request until the damper position is less than 85%. Else, if the damper position is less than 95%, send 0. I actually think I'm not going to include that. I think just hard coding this written spec probably the best move, so try to make that please. That is myself reading the actual spec to you, and please follow exact. Update only pressure, and we can do temperature logic next. Hey guys, back again. So I ended up just making these status traces, one for pressure, one for temperature, and this actually helped me verify that the code inside here is correctly. So like, for example, like the temperature status trace, 3 requests, temperature difference is 8 degrees, the cooling loop is 100%, and then here's the timers inside here that are calculating. So same thing with the pressure request, 3 requests if the damper is 95%, and the flow percentage between the set point. This one's calculating 41.2%, and if the actual timers are beyond 60, that's how we calculate requests. So here's our request output, and then we can actually manipulate these a little bit. So if I drop this down to 80, this should immediately go to 0, I think, because the spec does call for the, yep, there it goes, for the damper position on the VAV to be above 95% for it to start calculating requests. And then same thing with the temperature control points. This terminal load point, zone demand, sometimes is the cooling PID. Same fashion. So I'm going to drop you down to 20, and this guy should immediately start dropping off as well too, based on our 10-second internal timers in here. And it looked like it did not. So let's just start making our temp closer to, oh yeah, I know it needs to be within 5 degrees. So if I just put that down to 75, this should immediately drop down to nothing. Yep, there it goes. So I also put this use imperial because the spec does state for a difference between imperial units and metric. So if you toggle this false, it'll be using metric points inside there. So it'll just switch between metric and imperial. So that's all I have for this one. Next video, let's wire these into the air handling unit. The air handling unit, Guideline 36 program object.